Hello, I'm Kostas Bouglas, part of the coordinating team for ICCS, representing the RESIST consortium. Our consortium consists of 17 partners and 2 infrastructure users, hailing from across Europe and Israel. In this presentation, I will be talking about the RESIST project concept and objectives, the project progress and the research results so far, as well as how and where we will be validating our project. The field of transportation has seen great achievements with large important structures, but these structures, especially as the years pass, remain susceptible to extreme events, them being natural disasters or phenomena due to aging or even man-made incidents, and in time that everything is interconnected, cyber attacks as well. The RESIST project will be using flying robots in order to take measurements in critical road infrastructure, namely bridges and tunnels, using vision and contact inspection. It will perform vulnerability and predictive analysis of the structures, followed by risk assessment and management, in order to give the infrastructure managers the most accurate information possible. Additionally, it interconnects the users of the road, meaning the drivers, with the infrastructure owners, with the RESIST mobile application, and in order to reduce danger on the drivers and traffic congestion, it allows for multimodal rerouting congestions. And for the most extreme scenarios, RESIST has the capabilities of taking over the whole communication network of the affected area using the REDCOM node, which offers a variety of redundant channels ranging from satellite to LTE to even emergency calls. All of the above in one integrated platform and protected from the RESIST cybersecurity platform, which covers not only the network infrastructure, but field devices as well as meaning drones. The major concerns of RESIST is to protect users and ensure seamless mobility, and most importantly, avoiding any human and financial cost, to prevent, predict, and increase resilience by vulnerability and predictive analysis, as well as risk assessment and management, and to react, providing optimal information to minimize the impacts and restore services. It would take too long to talk about all the different modules and all the technological progress we have in RESIST, so we'll focus to the ones that are more recent. We have developed multi-rotor flying robots with sensor suites for bridge and tunnel inspection, which are now under testing. We have contact inspection robots, visual inspection robots, and ground control station, which helps control the robots. The visual inspection robot for bridges and tunnels is a commercial drone with multiple adaptations, listing some of them: propeller protection, gimbal for camera orientation stabilization, camera integrated on the top, vibration dampeners, electronic cover for dust protection, a LiDAR with different configurations depending on the field of view, onboard PC for custom flight control, and a commercial autopilot with advanced SDK interface. Our contact inspection robot, supplied by our partners in Gatec, is a new aerial robot design with reduced size and weight of about 40%, which is safer and easier to operate. It's got an octo-quad configuration, which is powerful and compact. We've made modifications on the robotic arm. We've moved the 4th degree of freedom to the end and then control the aerial platform using the 4th and 50th encoders information. That allows us not to use the magnetometer. Several mechanical modifications are ongoing to make the arm robust but lightweight. Again, this robot has been finished and is now under field testing. The contact is continuing with the previous robot, and we have a bit more changes. Propeller protection, which allows for flight extremely close to obstacles and is designed against light impacts. Aerodynamic fairing can be removed if electronics are too big. You can see a small video of some lab tests. The contact inspection robot for tunnels. We were thinking of confined spaces, and the robot has to be smaller and more compact for safety. It accommodates operating mode for a radiometric sensor, which is one of the sensors in our sensor suite. It's got increased power, meaning increased payload, compact design, maintaining the capability of lateral movements while applying lateral forces. Same tilted coaxial octorotor configuration. It's got an active rotating docking mechanism and Cartesian manipulator on center vector, allowing for improved accuracy and 2D scans. In the sensing part of the project, we have developed a custom 3D printed design as well as a working prototype of a photogrammetric visual sensor that uses 2 high-resolution industrial cameras with the MV Blue Fox 32124C, a crack width measurement suite, which is a suite of sensors for contact inspection that measure crack width and modulus elasticity. It's an optoacoustical ultrasonic receiver mounted on a multi-fiber fan-out connector to measure the crack width. The ultrasonic wave generated by the piezoelectric transducer is detected by measuring the deflection of the membrane as vibration of the optical power reflected from the cavity. In order to facilitate the integration of the crack width measurement system on the airpath, all the electronic components needed for the measurement were integrated on a single 4-layer printed circuit board. Finally, the vibration module, which is a wireless vibration sensor that is designed to be installed by the drone and not by human technicians. It is a small sensor network consisting of one receiver and several vibration sensors with specific addresses. In the mobility continuity system, we finalized the Resist mobile application, which you can download from Google Play, finalized the relevant protocols for both full and partial enclosure, finalized development of the Resist platform user backend, which is the place where the end user would use this process software. In the video on the right, you can see how a lane closure will affect a specific part of the road in our simulator. Right now, the Resist project is in its final testing and integration stages. Of course, there is more work to be done and many more tests to be run, which are unfortunately affected by the COVID-19 pandemic, especially since we need to run them outside the lab. Nonetheless, the Resist consortium is confident that it will proceed soon to our 2 pilots, one in Greece, in Bridge 39 in Metsovo, and in Italy, in the A32 viaduct and the St. Petronilla tunnel, where we will be testing the GPS-denied environment capabilities of our drones. Thank you very much.